our goal here is to figure out if given a material or given a loading, can we figure out if it will fall in one of these regions? Would it have first cycle yielding or have finite life or infinite life? And there are really two ways of doing this. So let me first specify the problem. Here, what we're trying to do is given sigma A, sigma M, so that will be the loading. Given the material properties, that will be SE, SUT, SY, we need to predict if the material will fail at, and there's three options. Option one is at n less than 1, that would be first cycle yield, cycle yielding. It could fail for n between 1 to infinity, that will be finite life. And the third option is it would never fail, n goes to infinity, that is infinite life. So our goal here is to predict if the material will, which of these behaviors the material will show. So there are two ways of doing this, two methods. Method one, let's say it's the graphical method. Okay, what we do is create the plot. Just set this up. One second, I'm going to set up the projector. It should work. It works. I have something which will work this time. Yeah. Okay, so there are two methods. One is in order to figure out which of these regions it belongs to. One is we create the plot above using SC, SUT, SY, then plot sigma A, sigma M, and determine which region the, okay, maybe this is a bit of it, right? Sigma A, sigma A, sigma M. Okay, so once we basically put, we create the plot using SC, SUT, SUY, sigma A, CM. Sigma A, sigma M would be some point, like say this one. And if you know that if the point lies in the blue region, then it is basically infinite life. So that's one way of doing it. The other way of doing this is to compute NF. NF is given by sigma A divided by SM, sorry, sigma A divided by SE plus sigma M divided by SUT. This is for sigma M greater than 0. So that's the factor of safety for fatigue loading if the stress, mean stress, is greater than 0, or it is SE divided by sigma A if the mean stress is less than 0. And then there is another one for first cycle yielding, which would be NY is SY divided by sigma A plus mod sigma M. Okay, so first, what we need to do is we need to compute NF and NY using these formulas. And the second step is to determine which region it belongs to, which I will write on the next page. Grab this. Okay, so now the next step, once you get NF, NY, the third step is to do the following. If NF is greater than 1, it's infinite life. Okay, or n tends to infinity, or it's the gray region from the plot. If NF is less than 1, but NY is greater than 1, let's check something. Yeah, NY is greater than 1, then this would be finite life. That is, n would be a number between 1 and infinity. It's also the blue region in the previous plot. And the third one is if ny is less than 1, nf is less than 1 and ny is less than 1, then this would be first cycle yield. That would be, I didn't quite draw that region, but we can draw it. So first cycle yield would be all this region. All the way there. So we'll call it the yellow region. So this is how you can do it without using the graphical or plots. Okay, I'll just show you how to do this with an example. So we'll apply this on the three examples. Okay, so a steel bar undergoes cyclic loading with nominal stresses at the notch location given as sigma max. So sigma max is given 40 kpsi. Sigma min is 20 kpsi. Stress concentration factor is 1.2. The material strength SUT is 100 kpsi. Yield strength is 85, so SY is 85 kpsi. And fully corrected endurance limit SE is 40 kpsi. Okay, so what we're asked is factor of safety assuming infinite life, NF, factor of safety assuming yielding, and actual region based on given stresses. That would be, is it in first cycle yield? So is n less than 1, is n between 1 and infinity, or n is equal goes to infinity? That's the last question, which of these regions it does lie in. So let's do this one at a time. Before we can compute the factor of safety using any method, we need to first figure out what the average and mean stress is. So the mean stress is always half of the max and min. So half of this would be 40 plus 20 divided by 20 equals 30 kpsi. And the average stress is always sigma max minus sigma min divided by 2. It is actually magnitude. So it'll be 40 minus 20 divided by 2. That would be 10 kpsi. Okay, but remember, there is also a stress concentration because this is actually where there's a notch. So the actual stress, I mean, I would like to put this as the nominal stress. Let's call that sigma O. So the actual stress This just shows it is nominal, right? The actual stress is going to be Kf times the nominal. So that would be 1.2 times 30. 36 kpsi, and sigma average is kf times sigma AO is 1.2 times 10, so that would be 12 kpsi. Okay, so now ready to compute the factor of safety. So A, you need to compute NF. We just go by the formula I wrote down earlier. It is S sigma A divided by SE plus sigma M divided by SUT raised to minus 1. So sigma A is 12, SE is 40 kpsi, plus sigma M is 36, and SUT is 100. So NF is equal to 1.52. Okay, next we need to compute the factor of safety assuming yielding, so NY. So for P, NY equals, the formula is SY divided by mod sigma M plus sigma A. So what I wrote here? Yeah, same thing. So SY is given as 85, and we have sigma M is 36, sigma A is 12. So 85 divided by, I think, 48 is 1.8. Okay, so that completes part A and B. The next question is we need to figure out the actual region based on the given stresses. So I'm going to show both ways of computing that region. So the first method is the non-graphical one, that's the easier one. So for C, we say that the numerical method. The numerical method, what we do is, and something which I wrote down here. Maybe I should have written down. The graphical method, I shouldn't put 1 and 2. The second method is, let's call that the numerical method. This is step A, this is step B. Okay, so we compute NF, and then based on, so NF and NY, and based on NF and NY, we are able to compute, figure out the region. So here we need to just figure out, since we already computed NF and NY, we already computed NF and NY, it's just a matter of fitting it here. So if you go back here, we see that NF is greater than 1, NY is greater than 1. So if you look here, we see NF is greater than 1, and we don't really need to check NY. So NF is greater than 1, which means that it should be in infinite life region. So that was very straightforward for our numerical method. Since NF is greater than 1, we would say it is infinite life, n goes to infinity. If you want to do the same thing graphically, this is how you'll proceed. So this is another way of doing the same thing. We basically need to make a plot of the, we need to make this plot. Okay, so for that, for this plot, we need to identify what SY is, what SUT is, and what SE is. And all these three things are given to us. SY, see, SY is SUT, SY, and SE is right here. I'm just going to copy it. Okay. So let's draw the Langer line first. Okay, let's assume that 1, 2, 3, 4, this is 85. SY equals 85. 1, 2, 3, 4, so it'll be here somewhere. So that's the Langer line. Next, we need to draw the Goodman line. For that, we need to plot 40 on the y-axis. So 40 would be approximately midway, somewhere here, maybe slightly lower. So SE is 40. And then SUT is 100 kpsi. That's approximately here. SUT is 100. So just join this. And then it just goes flat. Right. Langer line. Goodman line. Draw it with a different color. Let's say 100 is here. Okay, that's the how the whole portrait looks. Now we need to just plot what sigma A and sigma M on this plot. So remember, this is sigma M. This is sigma A. Okay, so sigma M is given as something we computed from this step. Sigma M was 36 and sigma A was 12. 36 kpsi. Sigma A is 12 kpsi. Now we need to plot this on this plot. So 36 for sigma M, it's somewhere, this is 85, this is 0, so it should be somewhere in middle. This would be 36, let's say, and then 12. Since this is 40, 12 sounds like it should be a third of the way. Here. So this looks like this is where the stress is. Okay, clearly this stress is in the region n between, n tending to infinity. Right, this anything below the Goodman line is the infinite region. So we can also verify the answer we got using the graphical method, infinite life. It's been verified. We also got the same answer using the graphical means. So that's one way of doing it. That's the other way of doing this. Now we can do the same thing for, well, there's another problem which sort of repeats this same thing. What I've done here in this problem is I've changed the stresses. So sigma max now is 60 kpsi. Sigma min is minus 20 kpsi. Kf is still 1.2. I've given you the same stresses for other things, 100 kpsi. Sy is 85 kpsi. And then Se is 40. So that's not changed. That's the same. We only have changed. I've only changed the stresses. So what will happen is uh, you're asked to find the same things. Find compute NF, compute NY, and the region, right? So the way we'll do this is essentially the same. I'll go through this rather quickly. Sigma M is half of sigma max plus sigma min. So 60 minus 20 divided by 2. 40 divided by 2 is 20 kpsi. Sigma A is, oh, this is nominal, by the way, half of sigma max minus sigma min. And this is with the absolute sign. So 60 minus 40, or minus 20 divided by 2. So 60 plus 20 is 80 divided by 2 is 40 kpsi. Now from this, we can compute the sigma m. It's kf times sigma m nominal. So 1.2 times 20. That would be 24 kpsi. And sigma a is kf sigma a nominal 1.2 times sigma a nominal is 40. So that would be 48 kpsi. Okay, we've got that. Now we're ready to start with NF. So NF is, since sigma m is positive, NF, the formula for NF is sigma A divided by SE plus sigma m divided by SUT is to minus 1. So that's sigma A is 48. SE is 40. Sigma m is 24. SUT is 100, negative 1. So NF is 0.69. B and Y is S. So this is, by the way, this formula is only for sigma m is greater than 0, which it is. Different color. Okay, so the formula for NY is SY divided by sigma A plus mod of sigma m. SY is 85. Sigma A is 48. Sigma m is 24. This comes out to be 1.2. So here is the answer for part A. Here's the answer for part B. And then the last part is to compute which region it lies. Okay, so last part, we have two methods of doing this. Method one is the graphical, we'll do the numerical one. That's easier because we've already computed NF and Y. So we have to see which of these three cases are true. We notice that NF is 0.69, NY is 1.2. So if you go back, we see that we have NF is less than 1 and NY is greater than 1. So it has to be finite life. So for part C, the numerical method, since NF is less than 1 and NY is greater than 1, we have n between 1 and infinity. This will be finite life. You could also do this graphically. Okay, now the good thing is that since the SY, SUT, and SE are the same for this problem, the Goodman and Langer line would be the same. So this same plot holds true. I can just copy this. Okay, what is not same is this point, the point which you're going to plot here. Now, what we need to do is figure out where exactly this lies. So we're given that sigma A is, for this problem, is 24, and sigma M for this problem is 48. So sigma M is on the x-axis. 48 seems to be, so 0 to 85. 100 is here, so it seems like it's halfway between here and here. So maybe here, 48. And then sigma A is 24. Now, it's a bit harder to 24, 40. So 20 is halfway. So it's not clear whether it's on this side or this side. Okay, so it looks like it's probably very close to the edge. We need to figure out which side it is on. If you do this with a graphing calculator, you'll clearly get the value, but how do we do it without a graphing calculator? Let's see if we can figure this out. Okay, so we know the equation of this line, Goodman line. It is sigma M divided by SUT plus sigma A divided by SC equals 1. Okay, so there's actually a very easy test to figure out which side it would lie in. Okay, so anything on this line, on the blue line, will satisfy this equation, right? Clearly, the left-hand side, if you put anything, any point on this line, this formula will be true. If you put anything on this side of the line, so let's say if you put 0, 0, so you just can try putting 0, 0. So you have 0 plus 0, right? And that is less than 1, right? So that means that this point, 0 and 0, is on this side of the line. If you put a very large value to sigma M, sigma A, let's say something over here, like a huge value, 100 and 100, so irrespective of, well, since it's very big, greater than SUT, you'll see that big number plus big number, this number will be greater than 1, this will be greater than 1, so that will be greater than the right-hand side. So anything on this side will satisfy this equation in such a way that the left side will be greater than the right side. So now all we need to do is just put these values. So remember that if we get, what's the best to do this? Let's call this A, it's called A. So if A is less than 1, it's on n goes to infinity, right? This region. If A is greater than 1, n will be between 1 and infinity. So we have to figure that out just by putting the values. So here we go. Sigma m is 48. SUT is 100. Sigma A is 24. SE is 40. So we can compute this, and we quickly compute that. 48 divided by 100, that's 0.48. 24 divided by 40, so it's 1.08. 1.08. So that is clearly greater than 1. So it's this, which is true. So the answer is this is true, and so n lies between 1 and infinity. It is finite life, just like what we predicted from the numerical method. That's my answer. Okay, then there's a third question. Okay, which is basically taking the same ingredients, same SUT, but I've changed these stresses. Okay, so this one, I would like you to try yourself, and I'll give you the answer. So try this yourself at home. Okay, these are the answers I get. NF equals 3.3, B, NY equals 1.8, and C, I get infinite life. Okay, but try it yourself. You can do it either way, using the numerical method, using the factor of safety, or you could use the graphical method I just talked about.